Until now, we've been looking at field extensions. Mostly we've been looking at the rational numbers sitting inside complex numbers or inside real numbers, and we've been looking at fields that lie above the rational numbers. These have been most of our concrete examples. However, we often need to look at more abstract situations, such as when we construct finite fields or when we study field extensions of the field of rational functions over a field. Then we do not have this device of complex numbers or real numbers to fall back on. So we can construct fields in a somewhat more abstract way. The simplest example is when you have a field and an irreducible polynomial. So let's take f to be any field and pt to be an irreducible polynomial in the variable t and coefficients in f. Then you can construct an extension e to be ft mod pt. Now remember that if pt is irreducible, if it's an irreducible element of a principal ideal domain, then it generates a maximal ideal. Because if there were a larger ideal, then it would be generated by a element that divides pt. And so if pt is irreducible, it would generate a maximal ideal. And since the ideal generated by pt is a maximal ideal, ft mod pt is a field. And so this is a field. And now in this field, let's see. So we have ft, and this maps surjectively onto ft mod pt, which is equal to e. So in here we have the element t, and we can look at its image in here, which we'll call alpha. Then what we have is that p alpha is, well, it's the image of pt. So let's call this map phi. It's the image of pt. And that must be 0 since pt goes to 0 under the map phi. Therefore, alpha is a root of pt. So in the simplest example, what we've done is we've started with a field and an irreducible polynomial with coefficients in that field, and then we've constructed a field extension where that polynomial has a root. This kind of a construction can be carried out in a much more general setting, and this is going to be the main theorem of this lecture, which I shall now state. The theorem is that suppose you have a field f and let pt be any ft be any polynomial in ft. Okay, then there exists a field extension E over F such that Ft is a product of linear factors in Et. We know, of course, that when we take a field contained in the complex numbers, the complex numbers will always serve the purpose of the field E. But in more general situations, we actually need to construct this field extension E over F. Let's look at a couple of examples before we go to the proof. So just to sort of reinforce the abstraction that may be involved here, let's start with F being the field with 3 elements, which is just integers mod 3. Since 3 is a prime, that's a field. And let's take pt to be the polynomial t to the power 8 minus 1. Okay, then pt, let's try to factorize it as much as I can. So it has a factor t minus 1. T minus 1 into t plus 1 is t squared minus 1. T squared minus 1 into t squared plus 1 is t to the power 4 minus 1. t to the power 4 minus 1 into t to the power 4 plus 1 is t to the power 8 minus 1. Okay, now you can easily check that t squared plus 1 has no roots in F3. So in fact, t squared plus 1 is irreducible. In F3T. So you can define E equal to Ft mod t squared plus 1. So let alpha be the image of t in E. So we have the map phi from Ft to Ft, let's just write F3 here, mod t squared plus 1, which is E. And so we'll take t and call its image alpha. Then what we have is that alpha squared equals minus 1, because alpha squared plus 1 is 0 by design. And so what we have is that t to the power 4 plus alpha is plus 1. This factor here, this last factor here, is equal to t squared plus alpha into t squared minus alpha. Now if you just study this a little bit, you will see that if you take 1 plus alpha the whole squared, then this is 1 plus 2 alpha plus alpha squared. But alpha squared is minus 1, so this is equal to 2 alpha, but 2 alpha is equal to minus alpha because 2 is equal to minus 1 in F3. So 1 plus alpha squared is equal to minus alpha, and minus 1 plus alpha squared, similarly you can compute to show that this is equal to alpha. So we have elements whose roots which are square roots of alpha and minus alpha. So this polynomial further t squared plus alpha and t squared minus alpha further factorize. So what we have is, let me just write it over here, this thing pt becomes t minus 1 into t plus 1, and then t squared plus 1, we already adjoined its roots there, plus alpha and minus alpha into t minus alpha into t plus alpha, and then we have 4 more factors corresponding to t to the 4 plus 1. So t to the 4 plus 1 is t squared plus alpha and t squared minus alpha, and t squared plus alpha has 2 roots, namely the square roots of minus alpha, which means that we will take t minus 1 minus alpha into t plus 1 plus alpha, and then we have factors corresponding to this, which is t plus 1 minus alpha into t minus 1 plus alpha. So pt factorizes into 8 linear factors over the field extension E, which is just F3T mod t squared plus 1. Let's look at another example with the same polynomial, but instead of starting with F3, we'll start with Q. F is Q, and let's take the same, pt equals t to the power 8 minus 1. And once again we have this factorization, just copy it from last time. T to the power 8 minus 1 is t minus 1 into t plus 1 into t squared plus 1 into t to the power 4 plus 1. And these polynomials t squared plus 1 and t to the power 4 plus 1 are irreducible over Q. Okay, you should think about t squared plus 1 is obviously irreducible over Q because it has no roots, and a quadratic polynomial is irreducible if it has no roots. This t to the 4 plus 1, you need to show that it has no quadratic factors either. But we don't really need to do that right now. Let's just do what we did last time. So first define E to be qt mod t squared plus 1. So this is a quadratic extension of q, and taking alpha to be image of t, in E we have alpha squared equals minus 1. And so again we can write t to the power 4 plus 1 is equal to t squared plus alpha into t squared minus alpha. Okay, it's not hard to check that t squared, that there does not exist any element x in E such that x squared equals alpha or x squared equals minus alpha. Well, to do this, a general element of E is going to be of the form a plus b alpha, where a and b are in Q, are rational numbers. And so you just write down this equation, x squared equals alpha, and what you'll get is a quadratic equation involving a and b. And using that, you'll be able to show that such a and b rational do not exist. Okay, I'll leave that as an exercise to you. What that means is that t squared plus alpha and t squared minus alpha have no roots, and therefore each of them is irreducible. So we could take one of them and let's just define. So t squared plus alpha and t squared minus alpha are irreducible, and so you take k to be et mod t squared. These are irreducible over E. So I can take t squared et mod t squared minus alpha. That's going to be a field because this is an irreducible polynomial, and let beta be the image of t in K. Then what we have is that beta squared equals alpha. And what we also have is that alpha times beta squared is alpha squared beta squared, but alpha squared is minus 1, so this is minus alpha. So beta is a square root of alpha, and alpha beta is a square root of minus alpha. Of course, minus beta is another square root of alpha, and minus alpha beta is another square root of minus alpha. And so what we get is that t to the 8 minus 1 is equal to t minus 1 into t minus alpha into t plus alpha into t minus beta into t plus beta into t minus alpha beta into t plus alpha beta. And this is a linear factorization of t to the power 8 minus 1 in this larger field K. Now the degree of K over Q is the degree of K over E times the degree of E over Q, and that's 2 into 2, so that's 4. I hope these examples have given you a feel for what we are doing here, and now we are ready to prove the general theorem. So proof of the theorem. Well, before we go to the proof of the theorem, let's just go back and take a look at the statement of the theorem. So the theorem says that if f is any field and a little ft is any polynomial with coefficients in the field f, then there exists an extension E over f such that the polynomial little ft is a product of linear factors. Okay, so you have a complete factorization of the polynomial in the field E. And so the proof of the theorem is by induction on the degree of f. Now if f is linear, then this is trivially true, right? So theorem holds trivially if ft is linear or degree is equal to 1. Okay, now if ft is irreducible, then just take as a first approximation, let's take E to be ft mod the ideal generated by little ft. And this is a field. It's an extension of f. And now pt has a root in, as we've seen, the image of t in E. So the image alpha of t in E is a root of pt. That means that pt can be written as t minus alpha times qt for some polynomial qt in et. Now we are working over E because this root is in E. So we apply the factor theorem in the field et. The factor theorem says that if you have a polynomial which vanishes at some point, then the polynomial is divisible by x minus t minus that point. Okay, so so this is the form of pt, and so let's write now ft. This is ft. And now what we can do is we have degree of qt is strictly less than the degree of ft. So by the induction hypothesis, there exists an extension k over E such that ft is a product of linear factors over, maybe I can't call it k, I started with the field k, so let's call this oh no, I started with the field f, so this is fine, linear factors over k. And so ft split is a product of linear factors in a field k, which is an extension of f, because E itself is an extension of f. Now suppose ft is not irreducible. Then you can write ft as pt times qt, where degree of pt is less than degree of ft and degree of qt is less than degree of ft, and pt is irreducible. Just take an irreducible factor of ft. Then again you define E to be ft mod the ideal generated by pt, and so pt has a root in E, and so we can write pt equals t minus alpha times rt. So what we have is ft equals t minus alpha times rt times qt. Let's call this st. So what we have is that degree of st is strictly less than the degree of ft, and working over E, what we have is there exists an extension k over E such that st is a product of linear factors in K. Well, St is a product of linear factors in K, and Ft is t minus alpha times St, so also Ft is a product of linear factors in K. So what we've shown is that you start with any polynomial over any field, you can always find an extension in which that polynomial is a product of linear factors.